recording? Well, let's just make, well, fuck it. There we go. Now it's not ready for children. Now it's not suitable for children. Perfect. Okay. So let's talk about new things first. New thing being hyperbolic trig functions. This is now recorded. Take a picture of it if you want. Is there a weight? Your weight cup. Good. Okay, so let's talk quickly about these. And these are on the web work review. So hyperbolic trig functions. It sounds so intense and awesome, right? Like hyperbolic trig functions. Oh, what? And the key is, you know how the normal trig functions are built on the unit circle? The hyperbolic trig functions are built on a hyperbola. And it's a hyperbola that fits really nicely with circle. So it literally is a hyperbola, you know, it's like x squared minus y squared equals 1, as opposed to x squared plus y squared equals 1. You don't really need to know that, but that's why it's called that. So it's like a relationship between some angle swept out here and then your x and y coordinates. Just like this thing where the x coordinate is your cosine and the y coordinate is your sine value on the unit circle. But there's a nice way to think of it. So this is hyperbolic sine. And I'm just going to define them for you. Hyperbolic sine. And so it like sinh. I think a lot of people call that just sinh. There's no C, but we kind of like added in. And the hyperbolic sine of x is actually defined to be e to the x minus e to the negative x, and then just half that. Cosh is the hyperbolic cosine, and that is the average of those two functions. So it all comes back to this really beautiful function that we know and love in calc, e to the x, the bestest of all. You can get pretty far with that, but best way to think of this is in terms of identities. It's defined as hyperbolic sine over hyperbolic cosine, just like tangent is sine over cosine. And then when you take the average of those two, the halves cancel, and you just get yield this. Yeah, let me give you some pictures. So hyperbolic sine, you could work this through if you wanted. Oh, that's a shitty horizontal axis. And now it's a shitty vertical axis. Let's just do the whole thing over again. Good. So hyperbolic sine looks like this. Looks a lot like an x cubed function. It's not. It's a lot steeper than an x cubed function. But it's got that similar feel. Hyperbolic cos is actually really important in engineering. So hyperbolic cosine looks like a parabola. But it's not. It's actually a shape called a catenary. And a catenary is formed, you can prove this using differential equations. Hopefully I'll see some of you in the spring in that class. But you can prove that this is the shape, that equation up there is the shape of a hanging chain. So if you just take a free hanging chain and hold the ends equal, it will fall in not a parabola, but in a catenary. So it's It's really interesting that that happens. This is also the shape of the St. Louis Arch upside down. That is a catenary. It's an inverted catenary. It's not a parabola. And the reason it's that way is because this is one of the most stable engineering structures created. So you'll see this under bridges a lot, this kind of arc like this. It's just incredibly resilient shape. So actually got lots of uses in the world. One thing I want you to notice here, some neat stuff, some calc stuff now. What is the derivative of hyperbolic sine? Let's do it. 1/2. What's the derivative of e to the x? E to the x. What's the derivative of e to the negative x? And negative e to the negative x. So that becomes a plus, right? A little frightening, the silence there, but that's all right. Does this look familiar, this formula? It's Koch. It's Koch, right? Isn't that nice? So the derivative of hyperbolic sine is hyperbolic cos. Just like our good old trig friends that you despise or just fear or whatever. Hopefully you don't despise them. What's the derivative of hyperbolic cos? So it's going to be 1/2. What's the derivative of e to the x? E to the x. What's the derivative of this? Negative e to the negative x, which is, what is this? Yeah, with no sign change, right? There's not the minus that comes in with the normal trig functions.
That's nice.
Isn't that lovely? Yeah. So they've got that property, this unique property that they're each, you can keep taking the derivatives and it just keeps alternating back and forth. A deeper secret to this is that if we allow this to be a complex number with the imaginary number I, this is the square root of -1. We're not going to do this. We don't do this. This is like a whole class. It's called complex analysis. But if you extend these functions to complex numbers, this is just a shadow of this. And regular cosine and sine are just shadows of this. They're just like little portions of the true whole reality. And it's just quite beautiful how it all works together. Let me do one more here. What about, I'll just do one more because I'm getting excited. I'm gonna do this derivative. What rule do I need to take this derivative? Solid, thank you. So I'm going to do the quotient rule. So it's the derivative of the top. And this just changes sign here, right? I'm going to do that. Times the bottom left alone. Minus top left alone. Times the derivative of the bottom, which is like so. And then over the bottom squared. So, wow, there's a lot of stuff to simplify, but it's going to turn out to be really freaking awesome. So I'm going to FOIL. It's e to the 2x. That's 1. Do you see how this times this is 1? That the I is 1? Because the exponents, you add the exponents. So e to the negative x times e to the x is 1. These are 1, so the O in the I of the FOIL is just the number 2. And then, then the L is e to the negative 2x, so that's the FOIL for that. And then minus, let's FOIL this beast. E to the 2x is the first. The outer and inner, again, become, what do they become? 2. Except minus 2 this time. And then the last one is e to the negative 2x. And then that's all over this thing. And I won't belabor this point. Do you see anything nice that happens on top? Cancel. So what am I left with on top? So the e to the 2x and the e to the 2x cancel, right? E to the negative 2x and this one cancels, so there's no more e's on top. But there is a plus 2, plus 2. You were close, definitely. And honestly, thank you for helping out and saying stuff. I really deeply appreciate it. Oh shit, what is that? Well, that is this squared. And what is that? That is 1 over this squared, and that is 1 over hyperbolic cosine squared. What's 1 over cosine normally? What's the other trig function? What's 1 over cosine? And it's secant? Secant? Yep, help out there. So it's hyperbolic secant squared. Just like the derivative of tangent is secant squared. This isn't surprising. So I just want to show you all these beautiful similarities come out, but you don't have the damn sign change. Pretty nice. So, all I need you to do is be able to, first off, just look these up on the table, and they'll be in the table. You know? But let's do some integration with them. So the integral rules work like this. They're sweet. Hyperbolic sine of u du is cosh u plus c. Hyperbolic cosh is sinh. Hyperbolic secant squared. I guess you say sec, something like that. Sounds like you say sex and you have kind of a lisp. Of u du is tenu. So for example, now I can do all sorts of things because I know lots of patterns. Really, I just need these patterns, and I'm just rocking it like crazy. Those derivatives and this together might not be bad to put these on your note sheet, but what if I had so I have this. So now let's just think. So we're experienced with calc and substitution. We don't freak out when we see things we don't quite recognize. We just take a deep breath and we think, okay, what are the rules? What are the rules for doing a fraction? I want to do substitution. What's a good thing to let u be in a fraction? Denominator. Who said that? So let u be the denominator. What's du? Cosh. Yeah. dx, yeah. Right? Look how pretty! So, you know, if I do my game where I say dx is du over cosh x, and I make the substitution here, this turns into freaking du over u. And that's freaking natural log. And that, when I back substitute, is quite easy. Yay. Everything's the same, right? It's all the same. We just need to know the basics of these functions. We need to know their derivatives, and that's about it. Let me give you one to do. Let's try. Your turn. So, what is the antiderivative, the integral? Oh wait, I've got like one written down here. Oh yeah, okay. So tangent, hyperbolic tangent to the 6th of x, hyperbolic sec squared of x dx. Use substitution. This is good practice. This is like, even though this is new, this is like good strengthening exercises. We moved up in weights at the gym today. tip, if you're having trouble, it turns into a power ruler. Rewrite it in a way that might make it a little easier on the brain. So when I look at this problem, I notice, I'm just thinking, here's tangent. I mean, you can think like trig-wise, right? The derivative of tangent's height is secant squared. Hopefully that's something that's kind of like in your brain, right? Like kind of part of your calc lore and calc heart. So this is like the derivative of tangent. So that like cues me off that, if I let u be this thing, then du is just this thing. And then this just all turns into that. Did anybody get this? No worries. It's the first time seeing this stuff, but you can do it. It'll just take a little warming up, so. Let's see, so that's our answer. I don't know how I feel about the looks. Okay. Well, I will there's a few of these on the web work. We can talk about them all you want, you know. Let's do another one. Let's try another one. Because what I really want you to get out of this is you can integrate anything now. Pretty close to anything. It's just a matter of shifting your perspective. So what if I gave you this? And let's pull away from this shit for a second so you don't get stressed out. I don't want you stressed out. That's even too much. That's even just like terrible. What if I gave you this though? This is not hyperbolic. All of a sudden you're really into these these normal trig fun, right? Like, oh, whew, there's no H. It's just the same shit. Just don't worry about sign changes when you have the H. Can we do that problem? Definitely thinking about it like that helps understand what the U substitution should be, I think. Okay. I am out of food. Oh, no, I'm not. help us out on what u would be here for substitution? Sine of 2x, right? Stuff inside these deep parentheses. And I know that cosine is the derivative of sine. So that really helps with that thought process. So this is going to be sine of 2x. Because what we're shooting, once we do that, we know we're looking at this, right? We're hoping for that form right there. So I play the game. Get some chain rule in there. Solve for dx. Make the substitution. So it becomes u to the 8 cos 2x du over 2 cos 2x. Those cancel, as I would hope. Got a 1/2 out in front. Power rule says that's just 1/9 out in front. U to the 9th. 1/18 sine of 2x to the 9th plus c. Questions on the, yes, Fernanda?
Where did the 2 come from? So the 2 cosine.
So the 2 came from the chain rule. So when I look at u and I differentiate it, I got the derivative, the outside is cos, leave the inside alone 2x, times the derivative of the inside. Does that make sense?
Yeah.
Spark that up? Yeah. Other questions? Okay. Let's do, let's kind of move on a little bit. We're going to be talking Friday and Monday about all this stuff. So you've got those days. I won't be telling you anything new. We'll just be coming in here and working together on getting you more integration practice. But it does look like a bunch more people watched the video from last Friday. So good, thank you. That helps. I can't tell who did, but a lot of people did. More than there are in this class. So whatever that means, I don't know. Let's look at partial fractions. Excuse me, no. Yeah, partial fractions. Number, the fuck is that? 15? Guess so, that makes sense. Okay, so we look at this. And we see a fraction, so maybe we try let u be the whole denominator. Is that gonna pan out for me if u is, does that pan out? Yeah, because du is 2x. There's no other x's in this problem. There's no way I can do that, so this is gonna fail. Then I realize, oh wait, there's a polynomial. So I have this integral and I have a polynomial over a polynomial. There is a good chance that this is a partial fractions problem, especially if I can factor this. So if can factor, then par frac. Is anybody in here Office fan? I've seen a lot of The Office. Oh fuck, I'm leaving. What is going on here? Anyway, then I can't talk about what I was gonna talk about, but I can talk about the math, so. So polynomial over polynomial, this is called a rational function when you have a polynomial over a polynomial. Rational function. Just means poly over poly. Big deal. Can I factor the bottom? Yeah. Do you know what it is, Josh?
Not yet.
Okay, cool. Let's all try to factor the bottom. Go for it.
X minus 5 times x plus 3.
Gorgeous. Thank you. You might have to factor a simple polynomial on the exam, so maybe you just kind of review how to do that. If you need help with that, I'll happily hook you up with some videos, so just let me know, and I will have Patrick JMT help you with that. I'm gonna go to YouTube Tutor. So, notice here I have a product in the bottom. So this is the key here. I have a product of simple linear terms. And different, simple and different. That's even more important. When I say linear terms, I just mean the x's to the first power. That's all I mean. So partial fractions is all about, well, we can't do this, but boy, if we could break this thing, this fraction, and hopefully this isn't the first time you've heard this. If it is, I can't help you. Can't change that anyway. But it would be so nice if I could break it into this and this, and I can do these in my head. Integral of this, natural log. Integral of this, natural log. Awesome. So if we can break it down into the sum of two things like this, we have got it made. Think about what it takes to add two fractions together. If you didn't know where these came from, and you added these together, what would your common denominator be? Well, it would be this, right here. And you'd have to multiply this one by x plus 3 over x plus 3, and this one by x minus 5 over x minus 5. But this right here is called the setup stage. So we assume that the fraction can be broken down like this. Our goal is to find the a and b on top that make it true. So our goal is to find the constants a and b. Anybody watch that video? What's my next step after setup?
Multiply x minus 5, x plus 3 on top and bottom.
Solid, Lou. That's it. Flatten this thing out. So you're going to multiply through by the original denominator, just like Lou was telling us. So multiply both sides by x minus 5, x plus 3. This is always going to be the way. I'm always going to multiply by the original denominator. And this is the flattening stage. There shouldn't be any fractions. So what I get is 1 equals a times the x minus 5's cancel, and I'm left with x plus 3. B times, now I'm just left with x minus 5. Let me stop. You please tell me if that makes sense. Yeah? Good? All right. So now, this is supposed to be true for any x. So I can pick whatever x's I want, and it better be true. So at this point, I'm going to now choose some x's. So choose some good x values. What would be a great x value that would make that right side simpler?
-3.
-3, solid, because that would kill this off, right? So that's what I'm looking for. The x values that make this thing just make my life better. So let's use x equals -3. And then I've got 1 equals dead, b times -8. And now I know what b is. How cool is that, right? That's amazing. What's another good x value? Not Lou. Solid, absolutely, because that'll kill the b off. And we'll find a. So when x equals 5, we got 1 equals 8a. So a equals 1/8. We're freaking done. So I rewrite the problem as now it's the integral of a, which is 1/8, over x minus 5, plus -1/8, that's the b over x plus 3, dx. Cake. Natural logs. So easy, lovely. So this is 1/8 log x minus 5 minus 1/8 log x plus 3. If you want to have some logarithmic jollies, I don't really hear a lot of people clamoring for that, but I'm going to do it anyway. This would be this. And I'm just using log properties here to make it pretty. not needed, but hey, you know, you got it, flaunt it.
Dr. G,
Yes.
could you go through kind of the other way to, like, the one where you do substitution instead of just putting in the value? Whenever you're trying to get
Can you explain a little bit about what you mean, Olivia? I'm sorry.
Oh, it's okay.
Like, do you have one written down that I did? Like,
Yeah. Like this one where you substitute instead of just putting in the value.
Oh, yeah. I wouldn't do it that way, actually.
Really?
I would recommend again. Oh, but I'll show you. Let me show you. So Olivia's saying there is another way to do this. So let me. I don't want to blow off your question. Let me
No,
go
it's okay.
because it's good to have double knowledge or multiple routes of knowledge. So Olivia's saying, and I must have done this in the video, I guess. I took this right-hand side and broke it down into, reorganized it. So I've got AX plus BX, so that's A plus BX. And then the constants are gonna be 3A minus 5B. So notice that this is a constant. And this is like the X coordinate. So there's no X on this side, right? There's literally no X appearing over here. So this must equal 0. And this must equal 1 if these two sides are the same. And this is what you're asking, right? Yeah. So then I've got A plus B has to equal 0. And I've got 3A minus 5B equals 1. So I have to solve this system of equations. And there's multiple ways to do this. If you're in linear algebra, you're doing this like all the time. But this top one says A is equal to negative B. So I could replace this A with negative B. Minus 5B equals 1. Notice I get negative AB equals 1. B equals negative 1/8, and A is the opposite. So A equals 1/8. Does that sound good?
Oh, yeah.
Yeah. So totally open to this. I find this faster.
It is faster.
It's way faster. Yeah.
I don't know why. I always like to do the harder ones. I don't know why.
I like it.
I don't.
then stop.
I know. I don't know why. It just makes
Stop
sense.
doing that.
But I'll practice the other one.
Let me give you one to try on your own. Okay. There we go. Please do that in. Won't expect you to factor anything but just simple quadratics, and won't be any tricks to them. What are the good x values to pick?
2 and
2 and
negative
2.
2 and negative 2, absolutely. In these partial fractions problems, especially ones like this where you had to factor and expect lots of natural logs to appear. Okay, I got one more I want to do. I got two more I want to do, of course. Yeah,
Does
Josh?
it matter which side the x minus 2 is under?
No, no, no.
Doesn't, okay.
No, sir. Can I answer any questions about that? And you just have to do a few of these. They're all, it's the same thing over and over again. Actually, with one, let's not do this.
I was
Yes.
gonna say.
Yeah, not quite, not this, I don't wanna do this yet, but I do wanna do this, put an X here. That. And this is the other thing, so there's like a lot of varieties of these partial fractions problems we could cover, and we're not going to. We're gonna cover two kinds, and this is all you have to worry about. One is it's a quadratic and I factor it. The other is, it's already factored for me, and it's repeated factors. So, right, if I were to think about this thing being a factorization of something, this is the factorization, so, but it's repeated factors, they're all the same, as opposed to the things we've had. So for this one, I can do partial fractions. The setup is different though. So the setup. I'm gonna say x over x plus 1 cubed. And you have to think, where could this fraction have come from if it's the sum of other fractions? Well, certainly that could be a denominator. But I could also, and I have to allow for this possibility, otherwise I won't be able to figure it out. I could have also had an x plus 1 squared in one of these fractions, and then to get from here to there, I would have to get a common denominator, multiply top and bottom by x plus 1. And then I could just have good old x plus 1 under there. And then this one would need to be multiplied by x plus 1 squared, or x plus 1 squared. But this is the most general thing that thing could have come from. Let me stop. Is that making sense on that setup? Cool. So once the setup is done, everything else is the same. Flatten, pick some nice x values, find a, b, and c. So we flatten. And just as Lou told us before, we're going to multiply through by this denominator. Bless you. So you've got x equals, and here you just got to be careful. This is the thing I'm multiplying by. So when I multiply that times this, it cancels completely with the bottom. And when I multiply this by that, everything cancels except one copy of the x plus 1, and then this times that is going to be c times x plus 1 squared, because because only one of these cancels out. So now, Olivia, I could go that route where I figure out, I multiply this all out and compare coefficients. But we're not gonna do that. You could though. And sometimes, as you will see when those of you who join me in differential equations, we will do this a lot more than we do in here. So I'm gonna pick my x values. What's a good x value? -1 is solid, right? It kills. So let x equal -1. Hell, I know exactly what a is, because that's dead and that's dead. So that was easy. Nice low-hanging fruit. What's another great x value? What's always a good x value? Solid, yeah, exactly. Right? So go for things that make it easy on you. So we got 0 equals a, which we already know what that is, but let's pretend we haven't written it out yet. And then plus b plus c. And since I know a, so since a equals -1, I have 0 equals -1 plus b plus c. Cool. Are there other nice x values? What would be another kind of not too bad one that makes these things nice here? You can pick anything you want. What about -2? Right, because then that makes x plus 1 -1, and that's kind of chill to work with. You could put x equals 10 here, and it's all good. You can't go wrong. You can just make life, more or less pleasant. But what am I doing? Not what I said I was doing. So then notice how this left side is changing as I change x. So it's -2 equals a plus b, I'll write this out, times -1 plus c times -1 squared. So we have -2 equals a minus b plus c. And I know what a is. So since a equals -1, this is -2 equals -1 minus b plus c. And let's put that over here with our buddy, bless you.
Thank you.
So these two equations together, this one, I hate the way it's written. That looks so much better. And this one, I don't really enjoy the way that's written. That's -b plus c, I'm gonna add 1 to both sides, equals -1. And now solve. Add straight down, you get 2c equals 0. C equals 0. What's b equal? If c equals 0. Oh. What?
1.
Yep. Perfect. If c equals 0, b equals 1. Either of those equations. So we're done with our decomposition. Our decomposition looks like this. And now we just got some pretty chill, fairly chill integrals. So I've got this thing equals, let's see, what was it? -1. And then b was 1. And then c is 0, so that's it. Carly, question? Or Fernando, question? You got it? Love it, love it. And when I say that, I'm not trying to call you quit talking. I'm just making sure, seeing if I can help. How do I do those? So how do I do those integrals?
It's just negative natural log of x plus 1/3.
These are not natural logs, in fact.
No?
Yeah, because, so let's talk about that. I love that thanks for coming and getting in there, you getting your hands dirty. But for it to be a natural log, the entire bottom has to be u.
Ah, okay.
So you can see how that wouldn't work out, right? What could I let u be in this integral?
X plus 1.
Yeah, let's try it, right? Let's make it look better. it never hurts to try things. So du dx, oh, holy shit, that is great, because this becomes integral -1 over u cubed plus 1 over u squared. Oh my goodness. I probably ought to rewrite those as powers so I can use the power rule. So if you have a fraction that feels like a natural log, but it's not, it's probably a power rule. More times than not. Knock it out in parts. That goes to, let's see, we have negative already. That goes to -2. That goes to -1. So this becomes 1/2. And I back substitute. I've got 1/2 x plus 1 to the -2nd minus x plus 1 to the -1st plus c. Kind of amazing what we can do. I think that's all I have to tell you. I think I should stop telling you stuff. It feels like I probably should have stopped about a half hour ago, but it's too much to tell. So how about, so that's really the last thing I can tell you besides like addressing questions and discussions that you all bring up to me. Let's just start working on one of the billion things we have to do. We have at least 41 problems plus whatever's in WebWork 3 to still do. WebWork 3 will be good to do now because there's partial fractions in it. Problem with the trick with the review assignment is I don't tell you what to do. There's not like a clear route. I'm also in my office before our class on Friday. If you need me personally, I have office hours online tomorrow. Sitting there in front of those in the camera. Yeah, well, better. Does anybody have stuff that they know they want to talk about right now, like because of web work, or you split, Kelby? Oh, okay. But you are gonna be going on Friday, right? For game? Okay.
Yeah.
No? Yeah.
So, yes, please.
Yeah, let me come here. Okay, so we got a fraction. There's, what's the first thing to try, maybe? No, not partial fractions, because that's not a polynomial.
No,
So,
it's not.
yeah, so only with polynomials. So, we have a fraction, and you've actually suggested this earlier today. It might be a natural log. So first thing I hope is it a natural log? Can you see that it is? Let u be the bottom. And what's the derivative of the bottom?
This sum is supposed to be negative sign.
Yes, 3x times 3 chain rule.
Times 3.
Does that make sense? So that's just a multiple away from the top, right? Because this is going to be -3. The derivative of the bottom is -3 sine of 3x. You're just missing the -3 on top, so that tells you you've got the right way. So you make that substitution and then let the things kind of work themselves out. Makes sense? Beautiful. Give it a shot. All right, good job. I'm here. Do you have anything?